We've discussed the basics of material models in 3D graphics, and our destination here will be to get to the physically based rendering or PBR material workflow. PBR materials rely heavily on the use of textures, however, so we best discuss texturing on our way to that topic. To summarize the entire topic into a single sentence, texturing allows us to associate bitmap imagery with polygons, such that when a polygon surface point is observed at render time, we can also obtain some sort of bitmap information corresponding to that point. So for example, just using this quick diagram here, if we were observing this surface point on a polygon during the rendering process, we would be able to determine, well, what part of a bitmap image is associated with that certain surface point, right? How many pixels and which pixels are located right here on the polygon itself. So that's really what texturing is all about. Of course, we use textures for many different purposes. We'll mostly get into that when we talk about PBR materials, but so far, these are the basics. We'll begin by discussing 2D textures and their two-dimensional texture coordinates. What we need to accomplish here is essentially a remapping of coordinates from the 2D coordinate space of a bitmap or raster image to the 3D coordinate space of our polygon model, right? So far we've been using the X, Y, and Z three-dimensional coordinate space to model 3D objects and store geometry, but we're actually introducing another coordinate space here. This is a two-dimensional coordinate space to use to define basically positions on a bitmap image, and we use U and V so as not to confuse these with X and Y of 3D coordinate space. So if you've ever done some texturing before in a 3D modeling program, well, the whole notion of a U and a V coordinate here should maybe jog your memory a little bit. And of course, yes, we will start talking about UV mapping here as the primary method that we use to just tell the program, well, what parts of a bitmap image to assign to 3D geometry. All right. And the technical explanation for how UV mapping works is actually pretty straightforward. All we're doing here is remapping two-dimensional values, any two-dimensional values here. Let's put a point right here. I'll try and keep this shape square just so that it makes sense. Let's just place down 3 points here on our bitmap image, just arbitrary points, doesn't matter where they are. And all we're doing is remapping these UV coordinates. So I'll just describe this point here using a vector with let's say U1 and V1. We're just remapping this point right here to, let's draw that line in there to say that this point has been remapped to some three-dimensional coordinate here with its x1, y1, and z1 coordinates. So it's just a simple remapping process that we're doing here. And we're going to go ahead and do this for all 4 points here, right? We have 4 vertices of this polygon here. We need to create a correlation between points in 2D space and points in 3D space. So what we'll have to specify again 4 points in our UV space as well. Maybe this one is at U2, V2, and this is going to get remapped to this point right here. This vertex, I should say. with x2, y2, and z2 coordinates. Okay, so that's all we're doing here. And because we have this remapping of values, or this correlation between values, again, at render time, if let's say we observe some surface point here, what we can do is we can just interpolate between these remapped values, right? First, we just say, all right, well, this surface point is on the polygon defined by these vertices. Well, I know where those vertices are, remapped to. I know where they are positioned on the UV map. Here they are, right there. And so then we can just interpolate. We can take this, let's call this x prime, y prime, z prime. We can just interpolate between these vertex positions, where they are defined on the UV map, and basically just find the pixel information corresponding to that point that we just observed on the polygon, right? It might end up somewhere around here after interpolating between these points on the UV map. All right, so over in Maya, we'll just take a more practical look at how UV mapping works. I just have a plane, a very simple object here in the 3D view, just a single quad polygon. And I also have my UV editor open on the side here. And so let's take a look at that same idea, this whole idea of remapping values from this two-dimensional UV space to our 3D coordinate space. And let's just make sure this all makes sense. To help us visualize what's going on here, I'm going to turn on this checkerboard pattern, which is commonly used in Maya to just confirm that there's no distortion on your UVs. But we'll just turn that on so that we can see just how this image in the or any potential image that we UV map onto the 3D object is displayed. So just quickly, right? This is the 0 to 1 space in UV space, right? We've got origin right down here, and we've got a U value of 1 on the right-hand side here, a V value of 1 at the top, and so this is what we call the 0 to 1 space. In most circumstances, our goal is to UV map the entire object such that all the mappings between this 2D space and 3D space are positioned inside the 0 to 1 space here. And then we generally work with a square texture, which of course fits the aspect ratio of this 0 to 1 space. But let's talk about these mappings just so we can clearly understand how this works in 3D here. I'll turn on that checkerboard again, and I'll go to, let's say, vertex mode here, and I'm just going to go ahead and select one vertex. I'm going to select this kind of bottom left vertex in 3D space here, and we can see, actually I'll just turn on my move tool so that we can see that vertex highlighted, or the remapped version of that vertex visible in the UV editor. And so what I'm also going to do is pull up the modeling toolkit here in Maya, just so we can see that the 3D coordinates, right, bottom right-hand side of my screen here where my mouse is, this gives us a handy preview of the 3D coordinates of this point in 3D space. So we can see that this vertex is located at negative 0.5, 0, and 0.5 on the z-axis. And right, so that's the 3D coordinates. And so we can see that this point has been remapped to just origin in UV space, right? There it is. It is, we can just temporarily turn off the checkerboard so that we can just see the point on its own, there it is. That point has been remapped to origin in UV space. Let's take a look at another point here. It is located in 3D space at 0.5, 0, 0.5. And, well, let's just move our view over a little bit here in the UV editor, and we can see that this has been remapped to into UV space to a value of 1 on the U axis and 0 on the V axis, right? So that is at the other side of the 0 to 1 space, right? And we could do the same thing here for the top 2 vertices. And by turning on the checkerboard again, we can very clearly see what this remapping results in, right? The entire texture available to us in this square 0 to 1 region of UV space. It's just this test checkerboard with these words on it, and this numerical code, right? Since the 4 vertices of this quad polygon are positioned at precisely the extremities of the outer limits of this 0 to 1 space, the entire square texture is visible on the quad polygon. All right, so let's actually go ahead and change the mappings in UV space here. So I'm actually going to turn on this image dimming feature just to make that checkerboard not quite as bright so that we can see the UV shells a little bit more clearly here. And let's actually go to face mode. Let's select the single face of this object, and let's just perhaps scale it a little bit. Right, so I'm going to scale it down so that the polygon, the remapped version of this polygon, as presented to us in UV space, I'm going to scale it down so that it only covers this U character here. All right, so back to vertex mode here. So really what we've done, again, just to stay consistent here and clearly show what we are doing, what we've done here is we've taken, for example, this vertex down here at its coordinates of negative 0.5, 0, 0.5, and we've remapped that to a UV value of, well, it looks like 0.1 to, looks like about 0.22 or 23, something like that, and a V value of 0.1, 2, 3, 4, 5, at just over 0.5 on the V axis. And you know what? Just in case it is a little bit confusing, I'm going to turn off the checkerboard just so that we can see the UV values a little bit more clearly. Sorry if that was a little bit confusing there. Let's do the same thing here for this other vertex. Again, in 3D space, it is positioned at 0.5, 0, 0.5, and we've remapped this value to a UV coordinate of, so this is about 0.395 or something like that on the U axis, and a V coordinate of, again, just over 0.5, maybe 0.51 or 2 or something like that. All right, so again, we've just remapped these 3D coordinates to 2-dimensional space, right? We can see each vertex and the correlation with the vertex in UV space. Now let's make this a bit more interesting, right? Keep in mind, we can create mappings between 3D coordinates and UV coordinates beyond the standard 0 to 1 space, right? What we've done here is remapped our 3D coordinates to values, within the 0 to 1 space, but we can go the other way as well. We could, let's actually scale this up a little bit. And I mean, we can already see what's happening here. Maya is actually generating more checkerboard patterns for areas beyond the 0 to 1 space, labeled accordingly, and so we can actually start to see what's happening here when we remap values, such as this one right up here. The the XYZ coordinate of negative 0.5, 0, negative 0.5, with this remapped to about 0.11 on the U-axis, and 1 point looks like about 1.7 or something like that on the V-axis, we can see that we have exceeded the bounds of the 0 to 1 space. And, well, what Maya's trying to show us here is that really the texture starts repeating as you exceed the 0 to 1 space. This is the standard behavior among 3D modeling programs. If you remap coordinates to UV coordinates outside the 0 to 1 space, you'll basically start repeating the texture that you're using. Another option is to just clamp the values at U or V equals 1, which gives a different kind of strange effect that isn't commonly used from what I'm aware of. But yeah, most often you'll see the texture repeating as you extend beyond the 0 to 1 space. Now, I mean, actually, this labeling system, this 1001 and then 1002, this whole labeling system we see in Maya's UV editor here has to do with another texturing approach called UDIMs, where we actually are able to position UV shells in an entirely different square region in UV space, right? Maybe within the range U equals 1 to 2 and V equals 0 to 1, right? So the whole idea with UDIMs is that we're able to actually use separate textures for different parts of our model, but we're not going to get into that in this course. It's a bit more of an advanced thing, but still it utilizes the same idea here, just of remapping 3D coordinates to two-dimensional UV coordinates. And the final thing we're going to look at here inside of Maya is just to keep in mind that it is possible actually to distort your UV maps, right? If I just grab any vertex, right? If I grab that final UV coordinate that we're remapping to, and I just arbitrarily move that, we can basically make it such that the Euclidean distances in 3D space, right? Let's take a look at the Euclidean distance between these 2 points. That is, well, that's exactly 1 unit actually. We can just tell by looking at the grid. But taking a look at that, as opposed to or compared to the distance between these 2 points up at the top here, we can see that, it's a square polygon. So 1 unit down here is going to equal 1 unit up here. The distance between these points in 3D space. And let's just take a look at how those points are remapped into UV space. Well, again, these points up here, again, maybe I'll just turn off the checkerboard for a second so that we can see what we're doing. These points up here, all right, so they're a certain distance apart. But these points down here, well, the mapping looks a little bit strange now. If these points are supposed to have equal Euclidean distances, as defined by the geometry in 3D space, we would also expect the points to have equal Euclidean distances in UV space as well. And, well, because they do not, right, because there is a difference here, we can see that results in the distortion of the UV map, all right? So anytime when you're UV mapping, of course, I'm sure that everyone, if you've done some texturing in the past, if you've done some UVing in the past, you'll constantly have been on the lookout for stretched UVs, any sort of distortions like this. There's many ways in which this can happen, and of course that's why we use a checkerboard to just verify that our UVs have been created successfully, right? But anytime you see stretched patterns like this, basically what's happened is that the Euclidean distances between vertices in 3D space do not match or are not proportional to the distances present in UV space, right? So this is the goal of UV mapping, to basically use the tools available to us. For example, I'll just go ahead and do a planar mapping here, planar projected from the y-axis, right? We use our UV mapping tools to get correctly proportional or UV mappings where the distances between vertices in UV space are proportional to the actual or true distances in 3D space. So we've just talked about 2D textures and their two-dimensional texture coordinates, right? Like U and V used to map a bitmap image onto a 3D object, but we can actually use 3D coordinates to store a texture as well. Might seem a little bit strange, but let's take a look at this alternative approach to storing texture information. Right, not as a flat image, as a two-dimensional image like this, but rather we could visualize a 3D texture as a volume of information, right? So this is not a cube, a geometry per se. This is rather a volume of texture information, right? Texture information that would be appropriate to store in this volume would be something maybe noise-based or something like clouds, right? That would be another good one, or like fog or something like that. Just variations in color data stored inside a volume, right? That's a good way of visualizing what we could store or what we could use a 3D texture for. All right. Now, typically, such a texture will not be stored in a file as, well, if you think about it, there are a lot of data points to actually store here, right? At least with a two-dimensional image, it's pretty reasonable to keep track of, just a grid of pixels. It's not too crazy, the amount of data we need to keep track of. But, right, if we imagine like every slice of this three-dimensional volume here being an entire 2D image, well, then things start to really blow out of proportion here, and it would quite quickly become unfeasible to store 3D texture information in a file. As such, usually a procedural algorithm will be used to just generate on the fly a texture value for a certain point in 3D space. So what we could have here is, maybe again, if this 3D texture is noise-based, maybe it would be some noise function which returns a certain color value given an incoming X, Y, and Z coordinate. Okay, so usually we would think of retrieving color values out of a 3D texture as just passing a 3D coordinate into a noise function and getting the value returned out of that procedurally. All right, so this is a great example, right? Using a noise function to, again, as I said, maybe generate like clouds or fog or something like that. As noise functions are particularly pertinent to storing cool-looking information in three-dimensional space, we're going to find that certain types of textures like stone, wood, metals, certain organic types of textures, again, in addition to like the clouds and fog that I just mentioned, these are very commonly simulated using 3D textures. All right, and do note as well that 2D textures could also be procedurally generated, right? That there's no reason we can't generate a 2D image procedurally as well. Even just thinking about that checkerboard pattern that is available inside of Maya, that's an example of a procedurally generated 2D texture, right? Quite easy to do, and we can definitely make use of those in texturing as well.